Hey everyone, Amin here with AI Plays. Today we're covering color space conversion. Before we get started though, I want to point out that if any of you have tried running this code on your own computers outside of Google Colab, you probably noticed it runs much faster than you see on my screen. That's because I'm using the free version of Google Colab, and that doesn't offer a very high computing power. My goal here is to show you that even if you don't have a lot of money or resources, maybe you can only access a library computer or a school Chromebook, that isn't a reason not to learn. There's now enough free resources out there that you can experiment with code of this level and higher without paying a cent. The code might take an extra minute or two to run, but if you want to learn and improve yourself, keep doing what you're doing, and keep doing your best. With that, let's begin. To recap, so far we've covered how a camera converts light into a bare domain image, how to correct dead pixels, how to compensate for black levels, how to adjust for lens shading, what an anti-aliasing filter is and how to apply one, how to apply auto white balance gain control, how to convert the bare domain image into a full RGB image, how to adjust the lightness scale to make a more visible image, and finally how to convert color spaces from RGB to YCBCR. Now, after all the various operations we've done on the image, especially in large-scale transformations like color filter array interpolation, the image has a lot of color-based chromatic noise, and a fair bit of shape-based luma noise. Now that we are in the YCBCR domain, we can address each type of noise individually, and in this series, we'll start with the color chroma noise. This is purely a personal choice, since both types of noises are handled separately on completely separate channels. It doesn't really matter which one you do first. In fact, in most cameras, the two types of noise are actually addressed at the same time using parallel processing techniques, and then brought together afterwards for compression. We covered what noise is in video 5, the anti-aliasing noise filter, and to briefly review, noise is any kind of unwanted artifact that appears in an image. For example, if you take a picture of a computer screen with your phone, you'll be able to see pixels blocking up, colors being misrepresented, and other kinds of stretching. The anti-aliasing noise filter addressed blocky edges using a technique similar to an average filter. Today we'll be using normal distributions to apply a different kind of filter on just the color channels to detect and adjust areas with odd colorations. Specifically, we'll be applying false color suppression techniques to both the CB and the CR channels. So what are false colors? How are false colors detected? And how can we suppress them? Let's start with what false colors are. Take this image of a bright red flower. This was taken in great lighting conditions by a professional camera, and you can see beautiful details on it with amazing precision and accuracy. Now, what happens if we add a little bit of color noise? To do so, I first convert the image from the RGB color space into the YCBCR color space. Note, the values of each channel right now are floating points between 0 and 255. Then I create a temporary NumPy array of the same size as the CR channel, and fill it with random values between 0 and 2. Next, I add the temporary array to the CR channel and clip all values between 0 and 255. Finally, I reconstructed the RGB image using the adjusted CR channel. In practice, all I really did was add a very small amount of color intensity to a few randomly selected pixels in the entire image. All of the code was also from the previous step. In fact, even if most pixels ended up getting the full change of 2, that is a less than 1% change in color intensity to only a few points. Despite that, have a look at the new image that's created. Our beautiful flower is now riddled with splashes of green and blue, and the hue of red across the flower is ruined as well. And these splashes of green and blue, but where they don't belong, these are false colors, and they appear in finalized RGB images due to often minute and isolated errors in the CR and CB channel. They become especially prominent because of the transformations involved in switching between color spaces. False colors can appear in images due to noise created by various steps in the pipeline, though some steps, like color filter array interpolation, are more likely to cause problems than others. Additionally, false colors can also be caused by photos taken in poor lighting conditions or due to overcompression. As a final note before we move on to suppressing false colors, I'd like to point out that this was a slightly exaggerated example to better see the effects. Although an error of plus or minus 2 is very reasonable and very possible, you generally not see this many of them. Additionally, this image is mostly just red, and all of the noise I added was to the red chroma channel. If you look at the surroundings of the noisy image a bit closer, on the sides and around the flower, you'll notice that there are few to no splashes of color that don't really fit, despite the fact that all areas of the image were given the same amount of random offset. In most cases, this is the extent of false colors, and suppressing them won't result in a very heavily visible effect. However, as we've mentioned in the past, ISP pipelines are not adaptive algorithms. They need to work for all kinds of images, so a module like false color suppression is important to have in your pipeline just in case someone takes a picture of, like, a flower with the camera you build. Now, before we can detect false colors, we need to understand the statistical model known as the normal distribution. Statisticians declare that data is normally distributed if the data is symmetrically divided on either side of the mean, and roughly 68% of the data lies within one standard deviation, 95% of the data within 2 standard deviations, and 99.7% of data within 3 standard deviations. The mean is the average of a set of data, and the standard deviation is a measure of how spread out the data is relative to the mean. To put it another way, a low standard deviation suggests that all of the data is very similar to each other, while a high standard deviation suggests that there are outliers within the data. If you'd like to explore this concept more in depth, look up the statistics empirical rule. To detect false colors, we start by extracting a section of the image around a center pixel, just like a filter. For this example, we'll use a 5x5 filter. Then we create a normal distribution, calculating both the mean and the standard deviation using only the surrounding pixels. We don't use P0, also known as P0, in the calculations for mean or standard deviation since we want to measure how far off P0 is from the rest of the values in the image. Then we can compare P0 to the other values using the standard deviation and mean. If P0 is within the mean plus or minus, say, 2 standard deviations, that means the value of P0 is very reasonable and is about 95% similar to the surrounding pixels. With millions of pixels in an image, we're not expecting there to ever be a huge jump in pixel intensity, so if there are no false colors, this filter is just going to pass over harmlessly. But remember, the false colors we saw earlier were created by single individual pixels with very slight errors that set them apart from the rest. If P0 is outside of our accepted range of values, that means it's an anomaly with an extreme value relative to its neighbors and needs to be corrected. When it comes to suppressing false colors, we could just simply set P0 equal to the mean of all of its neighbors. However, this method comes with one major issue. What if the false color is not at P0, but is actually at P12? The mean is now not a perfect measure of whether or not P0 is a false color. In fact, all we really know with our method is that a false color exists within the 5x5 section. Well, first off, again, since false colors are really just caused by minor changes, the mean more or less balances out with a filter as large as 5x5. Also, since we didn't include P0 in the mean calculations, we are comparing only P0 against the standard deviation. We do have some measure of confidence that if a false color exists, it's likely P0. Despite this, to ensure no damage or mistakes in extreme scenarios like our flower from earlier, we introduced soft updates. Instead of saying P0 is equal to the mean, we now say that P0 is equal to a correction factor alpha times the mean plus 1 minus alpha times P0. Alpha allows you to control what percent of the mean you want to accept in the change to the image, and what percent of P0 you want to preserve. Alpha is always a value between 0 and 1. In this way, even in the situation where there are actually no false colors, but a false color was flagged anyway because the filter was maybe crossing an edge, the value of P0 will not be ruined by a non-representative mean value. Now let's have a look at the code. The NFC function will take as input the CBCR image generated in the previous step, and it holds the CB and CR channels. It'll also take alpha to control the intensity of the soft update, and thresh, which controls how many standard deviations we want our accepted range to hold. We start by making a copy of the CBCR image where we can store the changes we make to the CB and CR channels. And then we use a for loop to allow us to apply these operations to both the CB and CR channels one at a time. We extract the image we want to currently work on, extract the dimensions for iteration bounds, and pad the image to allow corner pixels to have a full set of neighbors to work with. Then we can start on the main loop. First, we use NumPy indexing to extract the 5x5 region of the image we want to work with, and we extract P0 from the section and save it as a separate variable. Then we calculate the mean. Since we want the mean of the area excluding P0, we can't just use np.mean like before. Instead, we use np.sum over the entire area and then subtract the value of P0, which gives us a sum of P1 through P24. Finally, we can divide this new value by 24. If you really want to use np.mean, you could flatten the 2D neighbors array into a 1D array, then pop P0 from this array, and finally use np.mean on the new 24 unit long array. It doesn't really matter which method you use though. In any case, after we have the mean, we can subtract the mean from all values in the neighbors array, and then change the value of p0 in the neighbors array to be 0, and finally apply the standard deviation formula to get the value of the standard deviation without p0. Finally, we can detect false colors. This if statement checks if the given pixel is outside of our accepted bounds of 2.5 standard deviations from the mean. If it is, we apply the previously mentioned soft update to p0 and continue the loop. If p0 does not have a false color, then since we made a direct copy of the CVCR image in the beginning instead of using np.zeros or np.empty-like, we can just move on to the next pixel. That is to say, without corrections, p0 of the CVCR image is the same as p0 of the NFC image. After running the code with an alpha of 0.3 and a thresh value of 2.5, then converting the image back to RGB, you can see that there isn't really a heavy difference, and just like we mentioned before, that's an expected result based on the type of image we're using in this series. And that's it for today. Next time we'll cover hue saturation control. Have a good day.